let us do the following. Let us look at evaluation of some series, infinite series. We looked at recursion relations, let us evaluate some infinite series numerically by using again contour integration. And the most famous of these is the zeta function. So let us do that. So let us call summation of series. And what we would like to do is to evaluate this series n to infinity 1 over n squared. That is zeta of 2 and the value is pi squared over 6. Okay. Now what we would like to do is not just evaluate this series, specific series, but evaluate also all the other even zeta functions like 1 over n to the 4, n to the 6 and so on and so forth. So I would like to use a little trick to do that and evaluate not this series but a little more general series than this. So let us evaluate 1 over n squared plus a squared where a is some real constant. Real or complex does not matter at this stage, but let us call it a real constant, some real positive constant. So a greater than 0 just to be specific. So I like to sum this series as a function of a. So let us call it S of a equal to this. And we need to compute what this quantity is as a function of a and get a closed form answer if possible, and from that if I set a equal to 0 I should be able to get zeta of 2. Now one way to do this is to observe that this is an even function of n. So if I make n go to minus n, then nothing changes here. So I could immediately write this as equal to 1/2 summation n not equal to 0 and minus infinity to infinity 1 over n squared plus a squared. Okay. I just add all the negative n contributions and they are the same as the positive n contributions, and you will see why I am doing this in a minute. Okay. The next step is to say it would be very nice if this term appeared as the residue of some function of z, a complex variable z, at the point z equal to n. I want precisely 1 over n squared plus a squared to appear as a residue. So I need a function which is analytic, has nice analytic properties and has a simple pole at the point z equal to n where n is an integer and the residue should be equal to 1. But we already know such a function. We already know that if you look at this function pi cot pi z, this function has precisely that property because this thing here is equal to pi cos pi z over sin pi z, and it goes as z goes to n, any integer n, this thing has a 0, a simple 0. So it's got this whole ratio has got a simple pole, and this goes to pi times cos n pi, that is minus 1 to the power n divided by z minus n times the derivative of this function at z equal to n, which is pi times minus 1 to the power n plus regular part. So these factors cancel out and you have precisely what you want. So this function pi cot pi z has the property that it has simple poles at all the integers including 0, positive and negative integers, and at each pole the residue is exactly 1. Okay. So let us consider therefore a function f of z which is equal to pi cot pi z divided by z squared plus a squared. Let us consider this function. What are its properties? What do we know about this? Well, we know that it has simple poles at all the integers in z with residue 1, but then there is this fellow also. So the residue is in fact the residue is 1 over n squared plus a squared at the point, which is what we want. Okay. So it immediately follows that you can write this as equal to half, and then when I want to compute the residue theorem I have 1 over 2 pi I times something is the residue. So I want 1 over 2 pi I a summation n not equal to 0 minus infinity to infinity, an integral dz pi cot pi z over z squared plus a squared. Okay. I have to now specify the contour, and the contour I am going to specify is the following. Here is 1, here is 2, here is 3 and so on, and the contour is a contour around each of these guys in the positive direction, leaving out 0. Minus 1, minus 2 in this fashion, and let us call this is contour C3, this is contour C2 and so on, and this thing here is C sub n, a small circle around each integer traversed in the positive sense. You are guaranteed that that is equal to this, because each of these integrals is 2 pi I, that cancels this, times the residue of this function at z equal to n, the residue of this part is 1, and this thing here is just 1 over n squared plus a squared. So S of A is in fact equal to that contour integral, except that this contour contains many pieces now. But now you do the reverse trick. You can open this out a little more. You can bring it out here, you can bring this guy out here and join these two pieces in this fashion, because the intersecting portion, the two ends will cancel each other, and you can merge these two in this fashion, and you can merge the next one and so on and so forth. So eventually this whole thing 1, 2, 3, 4 etc. is a huge contour like this going all the way to infinity on this side, and all of them traversed in the positive sense, so it is in this fashion. Likewise, you can merge all these pieces together. There is minus 1, minus 2, minus 3 etc., and this is another hairpin contour which goes like this, and this one again is in the positive sense, so it is traversed like this. That is where matters stand right now. Okay. But you see, I can define, after all, what do I mean by an infinite sum? It is some capital N and then the limit as n goes to infinity. So I can stop at some capital N and then let n go to infinity. Okay. That is what is meant by an infinite sum in any case. Now the point is, yes. I made a mistake. Well, each of these guys goes, this is the positive sense always, so this is how it is here, and this one is again yes, absolutely, absolutely, it is this way, you are right, thank you. Yeah, it goes in the anti-clockwise or positive sense. Okay. So now what I do is I join two pieces together, so I add that big semicircle in this fashion. So this goes out and comes back on that side, and similarly here this guy goes out and comes back in this direction. The question is,
will there be poles at plus or minus I?
Pardon me?
There will be poles at I.
Oh yes, there are poles. There is a pole here at IA, and there is a pole here at minus IA, and a pole at 0. They are all simple poles, because this has a simple pole at the origin which we have left out in the sum. This has a pole at plus minus IA definitely. So there are 3 of these poles sitting here. Okay. All of them are simple poles. But the point is, this contribution and this contribution in the limit as capital N tends to infinity is adding a well chosen 0, because the integrand, you have to make sure of that. You have to make sure that the integrand actually vanishes at these points, because you are adding this gratuitously. It better be a 0 that you are adding in the limit, and it is, because this quantity goes like capital R, this goes like R squared, so there is a 1 over R. And what does cot pi z do? We have to be a little careful here, because cot pi z is of the form cos over sine. So, it is e to the I pi z plus e to the minus I pi z over the same thing, e to the I pi z minus e to the minus I pi z. So, whatever z does, and remember that z is actually imaginary out here. So, these could be blowing up exponentials, but the interesting thing is no matter where you are in the complex plane, if some exponent blows up, there is another one compensating it down here. So, cot pi z remains bounded always, unlike e to the pi z, which will blow up if z goes to positive real values, e to the minus pi z will blow up if z goes to negative real values, e to the I pi z will blow up if z goes to negative imaginary values, and so on. That does not happen with this cot, it is always bounded, and since this is always bounded and this guy goes like a 1 over r, we are guaranteed that these contributions actually vanish in the limit. But once you glue it on, this is a closed contour, and you can now do the reverse trick and shrink it back. You can shrink it as far as it will go, and what is this going to become? So, it is going to become, there is a pole here, pole here, pole here, and it has got to enclose it in this sense, in this fashion. So, it is in the positive sense, but that is the same as saying that it is enclosing this guy in the positive, in the negative sense, this guy in the negative sense, this guy in the negative sense, all of them enclosed in the negative sense, because now you can pinch off the intermediate portions and have just the 3 residues from these points. So, this S of A is given by that complicated expression, but it is just the residue at 0 plus IA and minus IA. And now look at it, is fairly straightforward now, because S of A equal to 1 over 4 pi I, and then each of these guys is in the negative sense. So, there is a minus 2 pi I times the residue of these things. So, let us put a pi, the residue at the origin, but the residue at the origin of pi cot pi z is 1 always, because this thing here has simple poles at all the integers with residue 1. So, that is just a 1 there, and then you put z equal to 0, so you get a 1 over a squared from the first term, plus the residue from z equal to plus IA. So, everywhere except the factor z equal to plus IA, you put in z equal to IA. So, this becomes pi cot I pi A divided by 2 IA, because all I did was to write it like this, z plus IA, z minus IA. So, when I am looking at the residue at plus IA, I multiply by this factor and put z equal to IA, I get a 2 IA from this, plus pi cot minus I pi A over minus 2 IA. Now, I multiply by this factor and put z equal to minus IA, so that gives me a minus 2 IA and a minus here. But the cotangent is an odd function of its argument, so it just puts a factor 2 here and I can get rid of this. Okay. And now we can start reading out what is happening. This is equal to, I should be careful now. So, this gives me a minus half, so 1 over 2a squared minus sign, and then a minus half, so that became a minus, and the half goes away in this fashion. So, it is equal to minus 1 over 2a squared minus pi over 2ia, and then cot I pi A, that is equal to cos, that is e to the I times I pi A. So, let us do this slowly, so I get, don't make a mistake, minus I times I pi A divided by 2, and then the sign is going to be e to the I pi A minus e to the minus I pi a divided by 2I. So, it is going to pull an I on top and that I will cancel against this I and give you this. And the next thing is this is e to the minus pi a, this is e to the plus pi a, and the same thing happens here, e to the minus pi a minus e to the pi a, but there is a minus sign here and this minus sign cancels against this. So, let us pull out the 1 over, let us pull out the pi over 2a times, once these two minus signs go away, this is equal to cot hyperbolic. So, this is cot hyperbolic pi a minus, I pulled out a pi over 2a, so I better put that back, 1 over pi, and that is the answer. That is the closed expression for arbitrary a, for real a, but we can now analytically continue in a itself to all sorts of values. Okay. So, it gives you a closed expression for summation n equal to 1 to infinity 1 over n squared plus a squared equal to this thing here. It is a very famous function. By the way, this function appears in a physical context. You are familiar with this. Where does it appear? Pardon me? Pardon me? It is the Langevin function. It is the Langevin function. It appears in a very simple model of paramagnetism. Yes, right. So, we know all about this function's properties for real argument, but this is now valid for all sorts of arguments, complex arguments included. What does cot z do as z goes to 0? What do you think it does? Cot hyperbolic. Well, it is cosh over sinh, but cosh is regular, it's just 1 at that point, but the sine hyperbolic is singular, it has a pole, it has a 0. So, this cot hyperbolic has a simple pole. Just as cot z has a simple pole at z equal to 0, so does cot hyperbolic at z equal to 0. So, the question is, what is the leading term? We need to find out, and then it must cancel against this, because I am going to let a go to 0. I know when a is 0, this is finite. You know the value of this is pi squared over 6, which is what we are trying to prove. So, I need to know what does this guy do as z goes to 0. The leading term has to be proportional to 1 over z, because it is a simple pole at that point. What will be the next term in the regular C? Proportional to what power of z? Will it be proportional to z to the power 0 or z squared? What do you think? What I am saying is, this is equal to some residue divided by z plus regular part, and this part will always have this behavior a n z to the power n equal to 0 to infinity near the origin, right. My question is, what is going to be the first term, proportional to what power of z? Z to the 1. Why? Why not z to the 0? You are right. Why shouldn't there be a z to the 0 term?
Because if you do cos by sine expansion, then
Sure.
it should go like the
Yeah, but why does it? Yeah, it is true. Why can you say, but why? What is the reason you can say right away there can't be a z to the 0 term? What sort of function is cot z? Even or odd function? It is an odd function, so it can't have even powers of z, right. It is an odd function. So, the first term must be proportional to z. Okay. Well, let us find out what this function is. Well, this thing here is cosh. You can sit down and compute the power series term by term, but it is really cosh z over sinh z, which is equal to 1 plus z squared over 2 plus dot 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 divided by this guy here is z plus z cubed over 6 dot dot dot. So, I take out a z, so it is 1 plus z squared over 6, etc. We want the leading term proportional to z. So, this thing you take it upstairs and it becomes 1 minus z squared over 6, the whole thing divided by 6. And now you combine these two fellows, all you have to do is to add half and subtract 1/6, and that is equal to 1/3. So, the whole thing goes like 1 plus z squared over 3 plus dot 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 divided by z is equal to 1 over z plus z over 3 plus higher order terms. So, the leading term is z over 3. By the way, in this theory of paramagnetism, this 3 will appear in the denominator and you have this susceptibility in the Curie law proportional to 3 kT in the denominator. That 3 is the number of dimensions in space in that application. So, this whole thing goes like pi over 2a, a goes to 0 of 1 over pi a plus pi a over 3 plus dot 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 minus 1 over pi a, which is equal to pi squared over 6. That is zeta of 2. Okay. So, it rightly gives you this answer at a equal to 0, it gives you zeta of 2. The value, as we know, is pi squared over 6. Let us go a little further with this. What would you do if you had instead of the series, this series, suppose you had the series n equal to 1 to infinity minus 1 to the power n over n squared plus a squared. What would you do then? There are series which alternate after all in sign. Whenever it does not alternate, this pi cot pi z was very nice. But what would you do if you had minus 1 to the power n sitting there? Clearly the way to do this is to look for an analytic function which has poles at all the integers, but the residue at each pole is not 1 but minus 1 to the power n. And what would that be? Well, we had cosine over sine. You notice the role of this cosine was to get rid of this minus 1 to the power n in the sine. So leave it out, leave it out, and then you consider, now you consider f of z equal to pi cosecant pi z over z squared plus a squared. Consider that function instead and do the same thing as before. You got to be a little careful about what happens at infinity, about this huge circle at infinity. You have to make sure that this thing actually does vanish both up and down, which it does because there is 1 over e to the pi z sitting in the denominator in this thing here, both in the upper and lower half plane. One or the other of the two exponentials in the sign will ensure that this contribution from that big circle, semicircle goes to 0, and you can use the same trick as before. But there is an even simpler way of doing this. I am going to leave this to you as an exercise to evaluate it using this function, analytic function. Go through exactly the same arguments as before. But okay. By the way, there is a simpler way of evaluating this. There is a simpler way of evaluating the zeta function itself. So let me give that example. So you can. So you have 1 plus 1 over 2 squared plus 1 over 3 squared plus dot 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 equal to pi squared over 6. Suppose you had minus 1 to the power n minus 1 over n squared, n equal to 1 to infinity, which is equal to 1 minus 1 over 2 squared plus 1 over 3 squared minus 4 squared, etc. How would you evaluate this given that? Is actually very trivial. How do you evaluate this? You add and subtract. You add and subtract this term here. So what you write is equal to, you add the whole thing, you get zeta of 2, and then you subtract twice this series. But then you pull out a 1/4 on this side, and then you subtract the series, and that series again the zeta function, right? So the whole thing is just 3/4 of zeta of 2, and 3/4 of this is going to be pi squared over 8. Okay. Similarly, suppose you had every odd term 1 squared plus 3 squared plus 5 squared, etc. That too can be evaluated by adding and subtracting the rest of it, right. So those series are fairly straightforward. Once you have one of these series, the others are all straightforward. The same trick can be used here too. So do that and check the answer for this against that. Now I ask, suppose you wanted to do 1 over n to the power 4, zeta of 4. How would you do that? How do you evaluate this series? What function would you choose to do it? Well, one thing to do is the following. One thing that you could do is to say, all right, I add this, I can compute this. By the way, you do not have to do that. You can even just do this directly. I did not have to do this direct at all. I could have done pi cot pi z over z squared. I could have done that without the a. I could have evaluated it. How would it have differed if I had done that? Suppose I did not want to evaluate s of a but s of 0, then I do not need to put an a here at all. I would have put z squared at this point, and what would have happened then is that there would have been a single pole at this point at z equal to 0, that is it, but it would be a pole of higher order. What would be the order of the pole? Third order, because there is a simple pole due to this factor and there is also a z squared here. I did the thing with the a squared simply because I wanted to show you that a more general sum can be done, and then now you can put a equal to 0 and you recover the original value at zeta of 2, but you do not have to do that. How do you do this? Well, one way to do this would be to say I do pi cot pi z divided by z to the 4, but it is a little messy because now you have a pole of 5th order at the origin. You got to differentiate this cot 5 times, little messy. On the other hand, if you did this, what would happen then? What sort of analytic function would you get? This would have become z4 plus a4 out here, and then if we did that trick as we did there, what would happen now? How many poles does this function have other than the pole? There is a pole at 0, of course. So when you finally do this contour trick and you pull out just a few contributions, you would have a pole, simple pole due to this at the origin. All the poles at -1, -2 etc. outside your contour on this side, but you would have 4 poles due to this guy. So at all the 4th roots of unity multiplying a, you would have had poles, and you have to evaluate the residues at those points. So that would be one here, one here, one here, one here, and you have to evaluate those residues. So either you evaluate 5 residues at simple poles, or you evaluate a 5th order pole at the origin, and I think it is easier to do the former. Okay. Do you think, can you think of any other trick by which you can find 1 over n to the power 4? Think of any other trick? Given this s of a, so you have to constantly look for tricks. And we know the answer here, pi over 2a, and there was some cot hyperbolic and then the Langevin function. Given this, can you think of any way by which you can get at this? Pardon me? Differentiate with respect to a, exactly. Use that as a parameter, differentiate with respect to a. Then this becomes n squared plus a squared the whole squared, apart from some other factor, minus signs and so on, and then you put a go to 0. So you can differentiate this with respect to a, okay, right. You differentiate once again, you get 1 over n6 and so on. So from this s of a, by continued differentiation with respect to a and then letting the limit a go to 0, which you have to do carefully, you can evaluate the zeta function at all the even positive integers. This turns out to be zeta of 4 and so on. Okay. What is the zeta of n approaching as n becomes large? What is a zeta of k? Let's call it zeta of k to the summation. As k becomes larger and larger positive, what is this series approaching? What does this approach? 1. It is approaching 1 exactly, just the first term, everything else is going to 0 very rapidly. So as you can see, you had pi squared over 6. How big is pi squared? Around 10, right? So it is like 10 over 6. Pi 4, how big is pi 4? Very close to 100, 90, 100, whatever. So this is much closer to 1 on this side. From above, it is approaching from above these terms, because these are all positive terms. So this thing here tends, as k tends to infinity, to 1. And like I pointed out, if you plot this as a function of k, at 1 it is infinite, and of course it is tending to. It is rapidly approaching, very rapidly approaching the value 1. Okay. We will write down what this zeta of k is, or zeta of z is, as a function of z, and then analytically continue it to the left of z equal to, real z equal to 1 a little later in the course.